Welcome everybody to the 4:30 live stream of the Tour of the Universe. This is hosted here at the California Academy of Sciences by the Morrison Planetarium. And I'm really happy to actually see everybody today because normally you can't see the presenter because we normally do our shows in the live, in the dome with an actual audience. But today, the main planetarium, Morrison Planetarium, is under maintenance, so it's closed to the general public today. So I'm in our special green, our live stream room. So we got some really cool stuff here. And I'm going to be doing our tour of the universe here today. And if it's your first tour of the universe, you're in for a special treat, folks, because this is absolutely my favorite show. Um, this is a show where we start off pretty close to the Earth and we zoom all the way out to the very edge of the observable universe. And we learn a few things along the way. And hopefully by the end of the show, you won't have an existential crisis where we are in space. By the way, my name is Christian. I work in the planetarium and been in the planetarium for a few years now, and this is hands down my favorite show to do. And I'm happy to have y'all here today. Let's see. Do we have to go over any rules? Not today. We don't have any live audience, and I hope you have a great time and sit back and enjoy. I'm gonna put away my face camera so that we can focus on the show and you can see more of that. But like I said, we're gonna be starting off pretty close to the Earth, and we're gonna be starting off at this amazing human feat here called the International Space Station, or the ISS. And we can see the city lights of the Earth down below, so we can see some cities. We're at the night time right now. And a lot of people tend to ask me, hey Christian, what is the International Space Station? I always hear about it in the news and articles, but I don't really know what it is. Well, that's okay, folks. I'm here to tell you a little bit more about it. So the International Space Station is a research facility. It's a laboratory that orbits around our Earth. And they conduct many different types of science experiments here. For example, some experiments they've conducted are things like what happens when you try to grow plants in space. Normally the roots need gravity to grow towards the center of the Earth, but since there's less gravity, which way do the roots grow? Another thing that they've tested out is what happens when you try to spark a match in space. Does the flame act the same? Does that act differently? And my favorite experiment they've ever conducted on the International Space Station is where they had two identical twins. One twin lived on Earth for about a year, the other one lived on the International Space Station. After that year, they compared and contrasted the two twins. Turns out when you live in space for a long period of time, you tend to age a little bit slower, but not only that, you also lose a lot of body muscle because you don't have as much gravity working on you while you're up here in space. So if you plan to live in space for a long period of time, remember to exercise daily. And right here on our live stream, the ISS looks really large here on our view, but it's not that big in actuality. The International Space Station is about the size of an American football field, so if you've never been to an American football game, you can also use the whole California Academy of Sciences, the museum I'm at right now. If you've never visited, definitely come and visit. It's a great place to learn. And also what's incredible is that the International Space Station is traveling at an incredible speed. It's going at 17,000 miles per hour, where it orbits once around the Earth every 90 minutes, and it experiences 16 sunrises and 16 sunsets a day. Whew, how romantic. And also this looks really far away from our planet Earth as well, but it's not too far either. The International Space Station is about 250 miles above the surface of our world. So 250 miles, that's like going from San Francisco to Santa Barbara, a nice little road trip to get away with the family for the weekend. So not too bad per se. But folks, the International Space Station is just the first stop in our tour of the universe. So we're going to start to slowly leave it behind. And by the way, 250 miles, this is as far as we put humans into space nowadays, because traveling into space is quite costly. You have to purchase a rocket ship or pay for all the rocket fuel. You have to account for all the food, water while you're up here, so the bill gets quite costly quite rapidly. But like I said, the International Space Station is just the first stop on our tour of the universe, so we're seeing it slowly fade away to the lights down below. And before we lose complete track of it, I want to add a nice little orbital path so we can see it. And it looks like we're flying just above the Mediterranean at the moment. We can see Italy off to the left-hand side, Egypt down to the south, and now we're able to see our entire planet Earth from this vantage point. And ooh, do I love looking at our planet. And by the way, I want to let you know that the space program that I'm using for this live stream right now is something that you can go home and download if you want to fly through space just like how I'm doing. The space program that we're using is called OpenSpace. So if you go to www.openspaceproject.com, you can come across the link and you can download this, and it's a whole lot of fun. And just to let you know, OpenSpace is an open software. That means anybody can add to it. So if you're a computer gifted person who knows code, you can add space models, and it's a whole lot of fun. So you can do a lot of stuff with OpenSpace. By the way, it's not completely finished. OpenSpace is still in its beta phase. So if we come across any glitches or anything, I'll point them out. Hopefully we can look past that, but it's such a great software to use. And if you're not the computer type of person, I'm kind of not, you can also use another alternative program called NASA's Eyes. Just like the human eyeball, just go to NASA's Eyes, search it on your favorite search engine, and you can come across it, and it's so much fun to use. But right now, we're using OpenSpace. But now that we got a sense of what we're using in here, let's make our way over to our nearest natural neighbor to us in space, the moon. And folks, we humans have been to the moon before. That was between 1969 and 1972, thanks to NASA's 6 Apollo space missions that brought a total of 12 incredibly lucky guys to walk on the surface of the moon. They got to conduct science, and of course they had some fun up there as well. They got to play some golf. But again, last time we sent humans to the moon was 1972, a little more than 50 years ago or so. But don't worry folks, we humans are making a return trip back to the moon in the next few years, thanks to NASA's new space mission in the works called Artemis. Pretty much with Artemis, NASA wants to send humans to Mars. But before we can send humans deep into our solar system, we got to figure out exactly how we're going to be able to live out here in space. So the moon is the perfect stepping stone to figuring out the logistics of doing that. And what's really incredible is that they're going to be sending the first woman to the moon, but not only that, they're also going to be sending the first person of color to the moon, but not only that, they're also going to be setting up lunar bases throughout our moon. Pretty much our technology has greatly improved in the last 50 years, so we're able to conduct much more science in a much more compactable size. And one place that we definitely want to set up a lunar base is the south pole of the moon. The reason why is because we found ice there, and that can be very helpful because we can melt that ice, pass electricity through it, separate the hydrogen and the oxygen, and both that stuff's really valuable when you're far away from home. So look out for any news about Artemis in the coming years. We humans should be heading back relatively soon. And I just got rid of the nighttime on the moon so we can get a look at the amazing features that we're seeing here. But I also want to let you know, folks, that there's this common misconception that people think that the moon's really close by. I mean, when you're seeing a moonrise, when it's really close to the horizon, the moon looks so big it feels like you can reach out your arms and touch it. But it's incredibly far away. The moon's about 240,000 miles away from our planet Earth. Whew, 240,000 miles? Some of the adults who are watching right now may have a car with that many miles on it. And if you take better care of your car than I do, you can even imagine driving to the moon if you drove for 4 months nonstop, going about 80 miles per hour. Although I wouldn't recommend it, the roads out there are poorly maintained. Hee hee hee. And from here on now, folks, we're going to need to use a more useful measuring stick because at this scale, using miles is kind of like using inches to describe the distances between cities because space is so big. So astronomers use a more convenient measurement known as light speed. And light travels at a mind-boggling speed of 187,000 miles per second. That's roughly about 300,000 kilometers per second. So while it took the astronauts more than 3 days to reach the moon, traveling faster and farther than any human has done so or since, well, it only takes light 1.5 seconds to cross that distance at the speed of light. That's kind of like a short pause in conversation. But at last, it's time for us to leave the moon behind, so everybody say bye-bye, moon. We'll see you later. And just like how we saw before with the International Space Station, we're going to see the moon start to slowly fade away. And just like before, I want to add some nice trails so we can keep track of everything, because again, space is incredibly large. So now we're going to see the moon start to slowly fade away, as well as the Earth's orbit. And all these other blue lines that you're seeing here, these are the trails, the planets. So we can see quite a few different planet trails within our solar system as we start to zoom out. And by the way, folks, on our journey today, we're going to be traveling much faster than the speed of light. We're going to be traveling at the speed of the human imagination, thanks to the help of computer models like OpenSpace, showing us the most accurate images and information available to us. And now the nearest star to us, the sun, should be coming into view. So here comes the sun. Do. And we can see the sun just off to our left right over here. In fact, let's focus in and get a better look at it, shall we? And folks, the sun is also incredibly far away. It's about 93 million miles away from our planet. 93 million miles, that's a good distance away. In fact, we can see our Earth just right over here. So in order for sunlight to travel that distance, it takes sunlight about 8.5 minutes at the speed of light. 8.5 minutes to travel that 93 million miles. And this is a really good concept to keep in mind, because even though space is large and light travels incredibly fast, it still takes light time to cross those immense distances. So for example, let's say we're looking at a star over here that's 70 light years away from us. We're looking at that star as it looked like 70 years ago, because the light that just reached us took 70 years to get to us. So when you look at really far away objects in space, it's kind of like looking back in time in a sense, which is really cool. But now that we have a nice bird's eye view of our solar system, let's do a quick refresher of what we have, shall we? So right in the middle of our solar system, we have our star, the sun, the biggest thing by far. The closest planet to the sun is going to be Mercury, right over here, incredibly hot and cold at the same time. Then we have Venus. It's covered in thick layers of clouds, and it is incredibly warm there. Also has acid rain. And the third planet from the sun, we have Earth. That's where we are. All of our friends and family live there. And then past Earth, we have the famous red planet Mars, just right over here. And past Mars, you notice this kind of empty gap in the solar system, but it's not empty, folks, because that's where you're going to find the main asteroid belts. You can find a billion asteroids in this region, so there's quite a lot of them. And then past the asteroid belt, you have the really big planets, the gas giants, the Jovians. We have Jupiter off to our left, the largest planet of them all. And then we have Saturn, famous for its rings, next. And then past the gas giants, the Jovians, we have the icy gas giants. We have Uranus, the funny one, and of course we have Neptune, the windiest planet in our solar system. And of course I can add everyone's favorite and lovable dwarf planet, Pluto. So here comes the orbit of Pluto on screen, just down below, right over here. And a lot of people don't realize that Pluto hangs out here in this outer part of our solar system called the Kuiper Belt. And I know a few of you are probably wondering to yourself, what's the Kuiper Belt? I've never heard of that before. Well, it's going to be all this stuff. Yeah, so a lot of things just appeared on our screen. And there's a lot more stuff out here in this outer part of our solar system past the orbit of Neptune. So the Kuiper Belt is like a second asteroid belt. What you're mostly going to find are icy asteroids and short period comets, comets that don't go too far away from the sun. And what's really incredible is that in the year 2006, our telescopes, our technology greatly improved, so we were able to see much smaller objects much further away. And in that same year, 2006, we came across more than 400 objects in that Kuiper Belt region, and some of this stuff was bigger than Pluto. So we couldn't call all these things planets. There was just way too many of them. So all the astronomers across planet Earth had a great big meeting. They had to figure out what exactly you need to be to consider a planet. And folks, that was the year 2006 that Pluto went from being a planet to a dwarf planet. And I know a lot of people still have hard feelings about it. I kind of still do. But that's the really cool thing about science, because as our technology improves, we're better at making better observations, so we can readjust, redefine certain objects. So that's one of the great things that I love about science. It's constantly updating and changing. But for now, I'm going to put away the Kuiper Belt region, because that's just a whole lot to look at, to be honest. And now on screen, I'm going to be adding the many different spacecrafts we sent out in the 1970s to explore our solar system. So on screen now we have the trajectories of Pioneer 10, Pioneer 11, Voyager 1, and Voyager 2. And the latest of them all, New Horizons, which did a quick flyby of Pluto in 2015. We can see this interaction just over yonder, down the bottom left of our right side of our screen. Now, just to let you know, all of these spacecrafts are all traveling fast enough to escape the sun's gravity and leave our solar system behind. But even the most distant of these robot adventures, Voyager 1, has not traveled as far as light travels in a single day. In order for sunlight to travel all the way out from the sun to the orbit of Pluto, it takes sunlight about 5 hours at the speed of light. 5 hours to get all the way out here. That's not too bad. But now, folks, it's time for us to leave our planetary scale behind us because now we're going to be heading out into interstellar space, the space between the stars. Distance now becomes so immense, it's going to take us roughly about 4 years at the speed of light just to reach the next star system to us, the Alpha Centauri system. And even though we're traveling incredibly fast in our space software, it still takes time to get to the next star system. And it looks like Alpha Centauri is going to be the star on our left-hand side. So again, we're right at the center. That's our solar system. And Alpha Centauri is going to be this one off to our left, right over here. And again, 4 years at the speed of light just to reach the next star system to us, folks. But that doesn't put into perspective of how long it would take us to travel there. Well, if you're getting a rocket ship of today's capabilities, make your way over to Alpha Centauri. It's going to take you about 8,500 years to get there. And that's just a one-way trip. Whew. Hopefully you pack enough supplies. But now, folks, we're going to stop and consider whether humanity has made its presence known beyond our solar system, because now we're stepping inside something called the radiosphere. And again, we're now inside something called the radiosphere, and this represents the current limits of the most distant radio signals humanity has ever broadcasted, or rather leaked into space. And it extends about 90 light years in all directions, emitting out from the Earth. This first began in the early 1930s with strong radio waves, early television, radar signal, and then later, the detonation of atomic weapons. All this stuff is emitting electromagnetic radiation strong enough to escape the Earth's ionosphere. And humans were broadcasting well before the early 1930s, but the earliest radio was not quite powerful enough to escape the Earth. Since all these signals are electromagnetic, they're traveling at the speed of light, so this is kind of like humanity's electromagnetic footprint in the universe. And of course, the radiosphere is constantly expanding at the rate of 1 light year per year, so is anybody out there listening? And now, folks, I'm going to be adding many different markers onto the screen. These markers indicate the many thousands of stars astronomers have discovered over the last 30 years, which has at least one or more planets orbiting around them. We call these planets exoplanets. And we're looking for any of them that are Earth-like with conditions suitable for life as we know it. So far today, we found more than 5,000 confirmed exoplanets in the nearby vicinity to us. 5,000 other worlds besides our own. And that number is going to be increasing as the years continue because we have space telescopes where their whole purpose is to find as many exoplanets as possible. In fact, as we're swinging around, you can see a large dense of exoplanets. So just on the very top of our screen right over here, you can see a lot of exoplanets in this one direction on the night sky. That's where we pointed a telescope in that direction for about 10 years, and we found a whole heap there. So you can imagine as we scan more and more, that 5,000 will be increasing. Now, to say if any of them are Earth-like with conditions suitable for life as we know it, well, we can't answer that question quite yet. But new space telescopes are being developed right now, so we've got a little while before we can answer that question. I mean, though they're on the drawing boards, they got to be built and then launched into space, and of course, got to be peer-reviewed. So again, we've got a little while before we can answer that one. But the more important point here is that quite a few of these planetary systems are within that 90 light-year limit of our radiosphere, and they could have potentially received our signals. However, since radio waves travel at the speed of light, if there is anybody that's out there able to listen in and answer back, the communication delays between hellos could be decades in time. Now, to give you an example, let's say we live on the far left side of our radiosphere. Let's say we're this star system. Let's say that's where Earth is. We find an alien civilization on the other side. Let's say this one over here. Well, we find a signal of life. We send them a message. It takes 60 years to get to them. They listen in, answer back. We wait for the response, take 60 years to get to us. Folks, that is a 120-year conversation in the making. Whew, and I can barely wait for a text message from my friend, so I don't know how that's going to work out. And of course, folks, planetary systems beyond the radiosphere, more than 90 light years away, have not heard from us yet, but eventually they will, as the radiosphere is always growing, but it becomes weaker as it does. And for now, I'm going to be putting away those exoplanet markers away, but I'm going to leave our radiosphere up on screen because as huge as humanity's electromagnetic footprint is, it is nothing compared to our Milky Way galaxy. All right, so we're now looking down on our Milky Way galaxy. We can still see a hint of our radiosphere, and I've got to ask for the folks who are watching at home, can you see your house from here? Probably not. And folks, our Milky Way galaxy is incredibly large. If you wanted to cross it from one side to the other, it's going to take you roughly about 130,000 years at the speed of light. Our Milky Way galaxy is incredibly large. And our Milky Way is so huge, we estimate that there's at least 300 billion stars in the galaxy. If our recent discovery of so many exoplanets just within our small neighborhood, within this vast star city is any indication, there could be billions of planets and potentially millions of Earth-like planets throughout our single galaxy. And before we leave the Milky Way, I want to show you what it looks like from the sideways perspective. You're going to notice that we live in a flat spiral disk. Kind of looks like a big pancake or a frisbee in space. And this is important because when astronomers and scientists want to learn about the universe, it's much more easier for them to point their telescopes galactically north and galactically south, instead of looking through the plane of the Milky Way, which has planets, stars, gas, debris, nebula, things that blocks their view of the universe. So keep that in mind. We like to point our telescopes galactically north and south. That's going to come important in just a little bit. But folks, the Milky Way galaxy is only one of many hundreds of billions of galaxies that comprise the known universe. So in this giant leap, every single point of light that you're now going to see no longer represents a star, but rather the location of an individual galaxy. Each galaxy containing hundreds of billions, perhaps trillions of stars. Now, we live in a local galaxy group, which contains about 30 galaxies large and small, also includes the nearest large spiral to us, the Andromeda Galaxy, only 2 million light years away, just next door, and it's heading right for us. We're going to get to know it pretty intimately in about 5 billion years, so mark your calendars. And as our picture continues to expand out, folks, you're now going to realize that galaxies are not evenly distributed throughout space, where there's one nice galaxy here in a nice neat line and another one here in a nice line. Instead, galaxies like to group together in large groups and clusters, or they avoid each other where they create voids in space. So we can see some nice galaxy clustering towards the center of our screen right over here. And if we zoom out just a little bit more, we can see some voids off to the left. So you can kind of think of galaxies like people. They like to hang out together, or they like to avoid each other. And by the way, folks, this picture that we're now looking at represents the closest 30,000 galaxies to us in a space over 300 million light years across. We got to give thanks to an amazing researcher by the name of Dr. Brantoli, who compiled this amazing representation over decades of time with the help of dozens of astronomers working aside him. So big shout out to Dr. Brantoli. I love flying through this galactic map. But now, folks, we have automated systems that are mapping into the most distant galaxies. So now we're about to see the large-scale structure of the universe. And remember, every single point of light that you're seeing, that's not a star, that's an individual galaxy. And by the way, the large-scale structure of the universe is not in the shape of a bow tie or a butterfly. Remember when I mentioned that we live in a big flat spiral disk of the Milky Way? Well, if I were to line it up, it would line down the middle just like so, vertically. And again, we like to point our telescopes galactically north and south instead of looking through the plane of the Milky Way. So that's why our large-scale structure of the universe kind of looks like a big butterfly. And eventually, we want our telescopes to be able to look through the plane of the Milky Way, but our technology hasn't gotten there yet. So hopefully, in the future, we'll be able to map out all these areas that haven't been filled in yet, so it's just a matter of time. And speaking of time, we're almost out of time, so let's continue pressing on, because now we're going to be encountering these really distant, faraway objects known as the quasars. And the quasars just appeared on screen as orange little dots on either side of the large-scale structure of the universe. And the quasars are short for quasi-stellar radio sources. These blazing objects are all billions of light years away, so now we're looking so far back in the depth of time and space that the most distant quasars represent the universe at a much earlier age. We're nearing the very beginning of galaxy formation. In other words, with the quasars, we're viewing a sort of awkward, gawky teenage version of the universe. And before there was a teenager, there was a baby. So let's press back to a time before quasars, planets, stars, and even galaxies began to form. Folks, we're about to see the very edge of the observable universe. And here we are, folks, at the edge of the observable universe. What we're looking at is something called the cosmic microwave background image, or the CMB image for short. All evidence indicates that the universe that we live in is about 13.8 billion years old. And this is data compiled by Planck and other radio telescopes. And this is a very baby version of the universe, only 380,000 years after the Big Bang occurred, where space and time began. And this is not your typical photo either. Instead, this is a temperature density image where the light echoes of the Big Bang are color-coded, with the lighter areas corresponding to the hottest, least dense regions, and the dark areas, the coolest, densest regions. So again, we can see some dark areas off to the side, we can see some lighter areas. And these differences between the light and dark are extremely tiny. They vary no more than 1 part per 100,000, so very minute differences. But these tiny differences eventually gave rise to that large-scale structure of the universe that we saw moments ago, that clumping and clustering of galaxies everywhere. Figuring out just how that happened is one of the larger challenges for cosmological research today. Folks, though our view here is of the outer edge of the known universe, the earliest light visible to us, that radiation actually persists all around us. It permeates the universe, stretching and cooling as the universe expands over billions of years of time. But folks, we've traveled as far back as the law of physics can physically allow us to go, so we only have one direction left. We're going to have to head back home, towards planet Earth. So let's find a nice entry point through all these quasars and galaxies, and let's make a return trip back to planet Earth, everyone. And for me, I like to take the scenic route, so let's fly through all these quasars. And as we're making our way back to our planet, we're across an expanse of over 13 billion light years. And we present you with this view of our universe in the latest in cosmological and astronomical information. We're covering eons and observing objects billions of light years apart. Now, we live in a golden age of astronomy with new generations of telescopes and spacecrafts that are extending the reaches of our eyes, preparing for the eventual race between the advancement of technology and the accelerating expansion of the universe. And with that thought, I want to remind you all that astronomy is for everyone. You don't need to be a rocket scientist to enjoy the beauties and wonders of our universe. All you need is the night sky, and if you can, get away from the lights of our cities and look up. Even a good pair of binoculars makes for a decent first telescope, and there's astronomy clubs all around the world that invite people just like you to look through their telescopes and peer into the great beyond, allowing you to partake in the wonders that our universe has to offer. Now, astronomy as a hobby can offer you an endless supply of satisfaction, and I do hope you'll join us, those who dream amongst the stars. But it looks like we made our way back into the Milky Way galaxy. We're flying right through this radiosphere. We're heading back to our star system, our little neighborhood in the vastness of space and time. And now we're about to pass those spacecrafts we sent out in the 1970s to explore our solar system, passing the orbit of Pluto in the Kuiper Belt region, and making our way back to the third planet from the sun, our homeworld. All the people that we know, love, ever heard about, or learned about in history, all lived on this one planet. And now, folks, we're about to pass the orbit of the moon. This is the furthest we've ever sent humans out into outer space. And as we make our final approach back to planet Earth, this is going to be the end of our Tour of the Universe live stream. And I want to thank y'all so much for stopping by and watching it with us this afternoon. But hey, look at that. We're back home safe and sound, just in time for dinner time. And that's all the time that we have for today, folks. And I hope you have a great rest of your evening. And thanks for stopping by. Have a great day, everyone. Take care.